We know quite a bit about the correlation, but thus far we've used it more or less qualitatively. We haven't used it in a computation, but it's very handy when you are trying to do a certain kind of estimation. So the topic for the next section is estimation, and we'll start out with the single variable case. So suppose you have a distribution of heights and you know its average and you know its SD, and somebody picks one of those people and says, estimate this person's height. What are you going to say? Now, we've had this conversation before. You could say 4 inches, but you're not going to do that. You are going to say 67 inches as the natural estimate. And we'll take a few minutes to examine in what sense this is the right thing to do. So if you say that your guess is 67 inches, well, the person is going to have probably some other height, and you'll make an error. And your error is the person's actual height minus your guess, which, since you've guessed the average, is the actual height minus an average, value minus average, also known as our old friend deviation from average. And you know roughly how big those are. Why do you know roughly how big those are? Because you know the SD. The SD measures the rough size of the deviations from average. And if you want to get precise about it, the SD is the root mean square of the deviations from average. So if you guess 67 inches as the person's height, then you can say you're going to be off by about 3 inches. And there is the first reason to be using the average, because you can give yourself a margin of error. And how can you use the margin of error? Well, no matter what the shape of the distribution of heights, you've got Chebyshev going for you. Chebyshev says that at least 75% of any distribution is in the range average plus or minus 2 SDs. And so at least 75% of your people will have heights that are within 6 inches of the average. So for these people, which is at least 75%, your estimate will be right to within 6 inches. Now, if you know a bit more about the distribution, for example, if you happen to know it's approximately normal, then you can say even more. You can say that 95% of the people will have heights in the range average plus or minus 2 SDs. So for 95% of the people, your estimate is going to be correct to within 6 inches, but that's if the distribution is normal. If not, you still know that that range is going to work for at least 75% of the people. So that's useful. But some among you ought to be saying, fine, so I know how to estimate using the average. What if I used some other number? So same problem. You have a distribution of heights, you know the average and the SD, and your job is to estimate, and you decide to estimate by some number, which I'm going to call C for constant. No matter who they pick out, you're not looking at them, so you're going to guess C. Well, you're going to make an error. And your error is going to be that person's actual height minus your estimate, which is C. So how should you choose C? Well, you're going to want to choose C so that you have a small error. And the best C, therefore, is one that makes the smallest error. Is there one? Well, for that, we need to do a bit of mathematics, which I won't do in Stat 2.1x, though I might write it out in a supplement. But it is a math fact that the errors will be the smallest, in the sense of root mean square size, if you choose the average as your guess. And that is the reason to choose your average. Not only can you say roughly how far off you're going to be off, you're going to be off by about an SD or 2 or 3, but you can't do any better than that. And that is why the average is called a least squares estimate, because it has the smallest root mean squared error. So that takes care of the problem when you are trying to estimate the value of a single variable and you know the average and SD of the distribution. What if you have 2 variables? So I give you a person's weight and I say, okay, so now that you know this person's weight, what's your estimate of height? You'd like to take the weight into account because you have this natural sense that weights and heights are positively associated. So if they've given you somebody with a relatively low weight, then you're going to guess a relatively low height, and so on. So that is going to be the business of the rest of the course. How do you make that estimate and what's the margin of error on it? But in fact, what you have to do graphically is very clear. So let's see in a picture what we're going to try and do. So you've got two variables, and the problem is this: given the value of one, estimate the value of the other. What we're going to do is easiest seen in a picture, and this is one of my hand-drawn pictures, of which I draw thousands on the board when I'm teaching at Berkeley. There's a lot going on in the picture, so we'll take it a little bit at a time. So there are two axes, one for the variable that is known and one for the variable that is to be estimated. Conventionally, the variable that is known is called x, and the variable to be estimated is called y. X is put conventionally on the horizontal axis and y on the vertical. You may put them on the opposite axis if you wish. Just every time I say vertical, you please think horizontal and you'll be fine. So supposing I have a scatter diagram and I have been too lazy to draw all the dots. I've just drawn the rough outline of it, and I have drawn a scatter diagram that is, you will recall, heteroscedastic, different spreads. Narrow here, wide here. And the game is this: I give you a value of x and you estimate y. Well, if I tell you that x is here, then you know that the point corresponding to this individual is one of these on this little strip here. So their value of y is from here to about here, and what are you going to guess? Well, you're going to guess their average, because you just have a list of numbers and you're going to guess their average for reasons we just talked about, and their average is going to be roughly the center of your strip, assuming no hideous asymmetries. And that's it. That's what you have to do. I give you x. You look at the strip on your scatter diagram corresponding to that x, and you pick off the center, and that's your estimate. So had I given you this x, you would have gone to this strip here, and you would have picked off its center, and there would have been your estimate. It's apparent from looking at these two estimates that one of them is better than the other. This one's better. Why? Because the strip is narrower, so in general you expect to make less error. And so in this one picture, we have summarized what we are about to put numbers to in the next few lecture segments, which is given a scatter diagram. How do I find the center of a vertical strip? And once we found the centers of the vertical strips, how do we measure how much we're off? And what we're going to do is stick to the simpler case where you don't have this difference in spread, rather where your scatter diagram is homoscedastic, the same spread throughout, which will return us to football-shaped scatter diagrams. And for this, I'm going to use your text. So here are the GMAT data that you've seen before. And there's a scatter diagram, which in this case has the verbal GMAT on the horizontal axis and the quantitative GMAT on the vertical. The red point here is the point of averages, whose coordinates are the average GMAT, verbal, and the average GMAT quantitative. These points that are yellow are the averages of their respective vertical strips. And why has that been done? But for the reason we said last time, that if you are given an x, you will go look at its vertical strip and your estimate will be the center of that strip. You can see that with this football-shaped scatter diagram, I remind you that football is the American football, the spread is roughly the same throughout, so we don't have that unsettling situation of narrow in places and wide in places. If you follow the line of these yellow dots, that is called the graph of averages, those yellow dots fall almost on a straight line. And here is a smoothed version of the graph of averages. And what we're going to do is we're going to identify what that line is. And once we've identified that line, then if I give you any value of x, you will just plug in to that line and you will get the estimate for y. That's the goal. For now, I'm going to ask you to ignore the names here, other than graph of averages, which you understand, but just to understand that the green line that has been drawn is a smoothed version of the graph of averages, and it is the line that we're going to try to use to get our estimates of y. It will be useful to know something about the football shape scatter diagram, which is that football shape is introductory stat speak for bivariate normal. And if a scatter diagram is football shaped, then that implies that the variable on the horizontal axis follows the normal curve, so you can use normal approximations for verbal GMAT. The variable on the vertical axis also roughly follows the normal curve. You can use the normal approximation for quantitative GMAT. And even more is true if you look at these vertical slices. Each of those is its own little data set, and each of those is roughly normal, as are horizontal slices. So, in other words, if you are told that a scatter diagram is football shaped, you can use the normal approximation. As to why that is true, well, that requires understanding of the bivariate normal distribution. That's a distribution on the plane, and for that you need to take a little bit of probability for now. If you are told football shaped, you can use the normal approximation. So just to summarize that, because we will be using it quite a bit, is that if you have a football shaped scatter diagram, you can assume that the distributions of both variables are roughly normal, as are the distributions within each vertical and horizontal strip.